Test, 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 audio. I see audio response. Audio response, yep. Hi guys, I think we lost the audio. Melissa, do you have to rejoin? And Melissa, you're telling?
I'm waiting for the link, but it's not loading yet.
Okay.
1 second. Yeah, I don't see it. Yeah, I'll text it to you. Thank you.
And you broadcast it out to the...
Yes, I will broadcast it to the students in the Zoom room.
I think that I can leave my ear pod in here, but it also, these things, I hate it. Mac tries to be too smart. If you take it out of your ear, it disconnects. But there's a setting somewhere that you can tell it not to do that, which I've tried to use unsuccessfully. Tell me when you have live stream again.
It's there, but there are only 9 people on so far. So
Melissa is broadcasting it out. Oops, is that the real?
No,
that's the old one. We're thinking here, waiting. So those of you who can hear me, the live stream audio dropped out and we restarted the live stream to get that back. How many live stream viewers do we have?
I did tell everybody several times.
So I thought we could get a permalink to our live stream. How come that's not happening? Every live stream is a different link. There's a way to create a permalink to your live stream. So let's look into that.
Okay, I think the best way is to, okay, there's 23. Should I just end all breakout rooms and tell them all?
Oh, yes.
Oh, yeah. Oh, absolutely. Yeah. Pull them out of the breakout rooms and talk. That's okay. You have time.
Okay.
You can also broadcast to tell everyone to get out of the breakout room.
Or like nobody's going.
Yeah, pull them out. Wake them up. I mean, they should know. They don't see it.
Yes, people are waking up.
Go ahead and make a full-on announcement. Can you speak with people yet, Melissa? Can you give people instructions?
Hi, everyone. Please click on the link that I'm sending, that I'm spamming into the chat. It's our new lecture. We're having some audio issues on the first one, so we restarted it. So new link.
They might have to cut and paste it in.
It is a link, but
okay.
If the link doesn't work for you, then yes, please cut and paste it into your browser, but it should be linked. You can't physically click or access the chat when in breakout rooms. Oh, I see.
Oh, so you were sending it to them, but they weren't getting it because...
I think they were just getting it as an announcement and then it disappeared.
Okay.
Now there are 70 people though. So.
Okay. Hi, everyone. Is my audio on? Hey, guys, coming back from that little short break. Had trouble with the audio. We're still getting used to this. We don't have all our equipment here. We ordered some equipment to keep this more stable. We're trying out half of it today. The half of it that didn't arrive is the audio. So we're trying to get away from me using this Apple product, iPod, AirPod. So hopefully next week we'll have all our equipment here and we'll have a smoother running system. I think most of you have rejoined. Apologize for that. who has control of the system? Oh, it's me. Okay. No, I will take it back. Okay, so A was very popular. So you guys are saying that you guys are saying, well, if I take this thing and I drop it on its side, I invert it, that should be the energy level diagrams for this spectrum. And actually, coincidentally, that works once in a while. Rarely, though, you do have to look at all the possible emission lines that occur, that are potentially occur. So I think what we'll do with this one, there are some of the possible emission lines that I've drawn in. Why don't we start one more poll, and with this information, see if you can tell me if A, B, or C is the correct answer here. So we've looked at the answers A, B, and C, and what do you think now? So go ahead, consider that for a minute. We have a poll running. Let's go to the poll, but just stay on that. This whole thing works much better, so we gotta like that. And I really like having the wire on the live stream. That seems super stable. Okay, I just wanted to have a quick thought on this. I think you can kind of see what's going on. So take a stab if you haven't so far. You know, if you got a friend sitting there with you, quick consult. We'll wait till we have 100 responses. Okay, 7 more of you. Push a button. We actually might have lost some people on the live stream debacle, so maybe we won't get 100. There we are, 98, 99, and 100. Let's see what you're thinking. Now you're very, you are saying B, which is the same thing you said. Oh, no, okay. Yeah. So you've switched. This was A, and that's what you're saying. And now you're saying B. I was messing up the answers with the questions. Okay, great. So I'll take control again. Ryan. So you're saying now that I've thought about it, I really do have to look at every possible transition. So I'll walk you through this. So you have in this option B, you have a long transition there. So that's high energy. And then you have this 4 to 2. So you had a 4 to 1, and a 4 to 2, and they're quite close in energy, 4 to 1 and 4 to 2. They differ only by this much energy. And then you have a 3 to 1 transition. But that 3 to 1 transition is actually the same energy as the 4 to 2. That's the same because this spacing is the same. They look the same. They are the same energy. So you don't get 4 lines from those 4. You get 3 lines from those lines there. Excuse me. 2 lines from those 2. So let me erase my drawings there. So this high energy one corresponds to the high energy line. This is lower, so this corresponds to the second line, but this one is the same energy as that one. It's coming from a different transition, but the gap is the same. So that one also corresponds to this one. So that one might have been twice as intense. Now this one is slightly lower than those two, so that. And then, of course, the red one, the low one goes here, but there's also this transition. Both of those are equal energy, so they appear down here. So that's the kind of analysis you have to do. And in general, you can't just tip the energy level diagram over and get the spectrum. So you have to look carefully at what's going on there. These energy level diagrams, reminiscent of a ripped six-pack on your those of you who are in very good shape, the ripples on your stomach. I, of course, University of California won't allow me to take off my shirt, but just trust me that I also have that ripped front. In fact, I have a 9-pack. I have 3 extra abs that other people just don't have. It's me and Lego Batman. So, and like I said, just trust me on that. So B is the answer there. So let's move on now. Question. Oh, okay. Melissa's telling me that I transposed the order. So the answer on the original one would have been A, sure. So this guy here used to be A. So I moved it over to B for some reason. Oh, I know why I did it. I moved it over to B because I wanted to put the right answer under this. But right, this was under A. Okay? Okay, so we're going to move on now. So we've talked about this quantization in one dimension, and it turned out to be pretty simple. And I kind of want to emphasize that again. There's not going to be a lot of math involving wave functions. In fact, I think I can safely say 0 math involving wave functions on the exam. What I want you to understand is the pictures and the concepts. If I have a waveform free in space, it can have any energy it wants. Once I put boundaries on it, then only certain wavelengths fit in those boundaries. And if only certain wavelengths fit, then only certain energies are possible, because each different waveform that fits has a different energy. So you get quantization of energies from a very simple wave-like property. You did not have to go to electrons and start investigating electrons. We understood all of quantum in one dimension without even mentioning electron. So we know that's where we're going, but let's just look in general. We can go, ooh, that looks a little bit off. So let's just add one more dimension, 2 dimensions. So again, I'm going to draw energy here on the board going up. I am not positive this slide is going to work. So here I've drawn a 2-dimensional standing wave. So this is like the surface of a drum or a tightly pulled sheet. And you can see it's oscillating up and down, just like the wave. Its constraints now are the edges of the drum. It has to be 0 there. So I've constrained the medium, and I have to get 0 along the ends. My waveform has to go to 0, so that fits in there. And that looks very similar to the waveform that we had for 1 dimension. So if I go to 2 dimensions, though, I pick up a quantum number for each dimension. So 1-dimensional quantum, we had 1 dimension, so we had 1 quantum number. 2 dimensions, I need another quantum number to describe all the states. So the states get a little more complicated, and let's look at that. So here I'm going to use two quantum numbers. I'll call them n and l. N will be just like we had, and l is the additional one I need. So that's just so I can tell them apart, n and l. If I go to describe the wave functions, I'll continue to use this idea of nodes. How many times does the wave function cross 0 within the boundary? And there are no nodes here because it's 0 at the boundary, but the boundary itself doesn't count as a node. It's only within the boundaries. So this guy has n equal 1, and I'm just going to start the L quantum number counting at 0 rather than 1. So n starts at 1, L I'm just going to start at 0. We'll see why that is in a minute. You can start with L at 0 because L isn't going to be exactly correlated with the energy anymore. N is exactly correlated with the energy, so we usually don't let it go to 0. So let's put in then a second level for n. So this is n equal 2 now, and n equal 2. Now this looks similar, again, to the one-dimensional wave. This one looks like it has a full wave standing in there. But of course, it has to stand in both dimensions. So it looks a little different. So I'll have, in this case, the quantum numbers 2. So n has gone to 2. L, I'm going to keep at 0. I'm going to start counting L equals 0. But in this case, I have one node, and the node is a radial or a circular node. So the wave function passes through 0 there, and you can see as it's oscillating, it has to go through 0 circular region. I'm going to add a second form, and why am I doing that? Because this idea of having one node is when you get to 2 dimensions, you can have different kinds of nodes. In 1 dimension, we could just have points. So all nodes were the same. But now we can have different kinds of nodes. Here I have a circular node, but over here, I have a planar node. That's linear, that's planar. I'm calling it planar. I've drawn a line, but it's a whole plane bisecting that drum. We're only in 2 dimensions though, so I've drawn it as a line. The dimensions up and above don't mean anything. And I know what you're saying. Well, the dimensions up and down don't mean anything. Why is it going into the 3rd dimension? All that means is that is the intensity of the wave function in that region. Okay, so I could plot it all out in, say, colors on the right on the flat surface. I could write this. So I have my circle in 2 dimensions, and if I wanted to indicate that the wave function has a node, I'd say, well, let me draw blue here, and I'll let blue represent negative areas, and then I'll let another green represent positive areas. And wherever it changes from blue to green, it went from negative to positive, so it had to go through 0. So this is a representation of what's going on there. High fluctuations in the center, these fluctuations on the outside, and right around here on the boundary between plus and minus, I have a node. So we can continue this thought. Equal energy waves are degenerate. Now, n is the same for these two. So these two have the same energy. And when I say degenerate, I mean of the same energy. So degenerate waves, here's the n equal 3. And you see n equal 3, I've picked up yet another value of L. So now I have 2 nodes, and I have L equals 0, so 3, 0. So n equal 3, L equals 0. I have 3, 1, n equal 3, L equal 1, and I have n equal 3, L equal 2. It turns out the maximum level of number of L is the number of nodes. And that's why I started numbering at 0. This one didn't have any nodes. So I'm keeping track of the maximum possible number of nodes, or the maximum possible modes. To say nodes and modes doesn't matter. You guys just focus on nodes. These are modes of vibration. They're characterized by how many nodes and the kind of nodes. So again, I have 2 radial nodes here, and then I have 2 combinations where one is radial and one is circular, and then 2 radial nodes, angular line nodes here. So I said that with babbling, so let me go again. 2 radial nodes, and I have 3, 0. I have a line node and a radial node, that combination, L equal 1. And here I have angular, 2, 3 are the quantum numbers. So notice, and be careful, this one is called 3, 0, but it has 2 nodes. The number L itself, there are several values of L. So there's value L 0, 1, and 2. The maximum L can be tells you how many nodes there are. And then just counting, you can assign an L to each one of them. And we won't go into how that's done, but L is going to delineate the 3 of those modes by the number of nodes, but they all have 2 nodes, the value of L. Question?
How are planar and angular nodes different?
I'm sorry, I'm saying planar and angular. That's the same thing. Sorry. Let's talk about that in a few minutes. Or maybe we'll just push that down the road.
Also radial.
Radial is more obvious because radial is a circle. Okay, I'll give you. Radial means a node at constant r, constant radius. Angular means, like you might think, nodes at constant angle. So if I had an axis here, if I define some kind of axis here, and I don't like that axis. The good thing about science, I can choose any axis I want. So I'm going to choose a slightly different one. I'm going to choose Y and Z like that. Okay, so this is Y, this is Z. This plane here is at a constant angle from Y. That's why we call it an angular node. But it can extend up the Z axis as long as I'm a constant angle from Y. So it could be a plane if I wanted it to be. But what's constant is this angle. Okay? There's a demo down there. I'm almost afraid to start them. I think these are easier to start, but I'm going to push it down kick the can down the road on that. There's some others that we'll try to start later. So one other thing to note, the more nodes, the higher energy. And that's going to be true as we move through all of our study of quantum mechanics. And you can see that already. 0 nodes, 1 node, 2 nodes going up in energy. And we talked about that in 1 dimension as well. So let's go. Now we've reached our destination. What we wanted to do was get to describing atoms and molecules. So far, we could have just been describing strings and drums, but they're just waves. And I did this, I kind of laboriously did this to get you the impression that quantum mechanics is not a crazy thing that came out of nowhere. Quantum mechanics came from, oh, that electron had a wave. We did this experiment and we detected a wave. What if we applied the things we know about waves that matter? And then we started to see, well, there'd be the uncertainty principle. There'd be the fact that if I know exactly the wavelength, then I can't tell anything about the amplitude. The amplitude looks the same everywhere. But if I use lots of wavelengths, so there's an uncertainty in the wavelength, I can arrange it so I know exactly the position. I can get the amplitude in one place. And then we also said you could have standing waves and count their wavelengths and get different energies. Just put boundaries on them. So those two things happen with strings and drums. They also happen with electrons, and that's what we were hoping. And it's interesting to note, historically, when we start solving these wave functions, you can write down the mathematical equation, and you would call it a wave function, for those standing waves on the strings and the drums, and even in 3 dimensions. And those mathematical equations were all solved way before quantum mechanics came to be. In fact, we're going to look at orbitals. We're going to look at the wave functions in an atom. The mathematical functions for those existed way before that. These kind of conical and geometrical sections and solutions to differential equations, that was happening, just after Newton. So 1800s, people were doing this. So we had the solutions to electronic atomic wave functions before quantum mechanics was even there. We just didn't know we needed them because we didn't know the electrons were waves. So this is just, through all of history, this has just been, we know a lot about waves. We've always known a lot about waves. Suddenly, matter is behaving like a wave. So let's apply those conditions to the waves. So now we are going to go to 3 dimensions. So now I have my XYZ axis, and I'm going to define the position of electron in terms of 3 coordinates. I'm not going to use X, Y, and Z. You can use X, Y, and Z, but I want to use 3 different parameters. As long as I use 3 parameters, I can locate it in space. So this has XYZ coordinates, but I'm going to use 3 different ones. I'm going to use R, and R is the distance from the center of my out to the electron. That specifies how far it is from the center. That's one coordinate. Then I'm going to use another coordinate, theta. That's the angle from the X, or from the Z axis down to that little vector that's pointing at my electron. That fixes it. So now the electron, so let me give us another, so the theta and R together, they fixed it, but now it can still be anywhere along that cone. So I haven't totally fixed it, but I'll take this angle theta now, and that's the angle from the positive x-axis of this vector. And now I'm going to fix it into this plane. So now it has to be the intersection of this cone and this plane, and it has to be right there. So those 3 parameters fix tell me where the electron is. Just like it also has an X, Y, and a Z. It turns out we do this because the problem itself is spherical that we're trying to solve, and the axes X, Y, and Z are not. So these are manifestly radial, manifestly spherical. R is sweeping out. All you do is taking R and you're sweeping it out in every possible direction. And when you do that, you would trace out a sphere. And we know that's what the atom is going to look like. So we choose a convenient coordinate system. If you're very good at math, so ask Jiho, you can transpose quantum mechanics from r theta phi to xyz with parametric equations. It's an exercise in futility, but it can be done if you just want to just like flex your math muscles. So r theta phi just make the math easier, essentially. So since I have 3 dimensions, I'm going to have 3 quantum numbers. I'm going to call the quantum numbers n and l, using those before. I'm going to add another one, m sub l. Okay, 3 quantum numbers because I have 3 dimensions. Like I said, we're not going to solve this. I have a animation where I can show you them, the various waveforms. We'll see if we can make that run. N we're going to call the principal. Is it really spelled principal? Isn't it PLE? Oops, little spelling error there. It doesn't matter. You get the idea. This should be LE, principal quantum number, not principal quantum number. The principal quantum number, meaning the most important one. N still gives you the overall energy of wave functions around this electron, around this center. And that again is going to be counting numbers, integers 1, 2, 3. And the boundaries, we said, well, I have to have a wave bounded by something in order to get standing waves. So what's bounding the electron? What's saying you have to be close to this center? And we know that for an atom, because for an atom, and we talked about this already, there's a plus Z charge here. That's Z is the atomic number, the number of protons. So there's a plus for every proton in there. So there's a plus Z here. And if we're talking about just one electron, a hydrogen atom, there's minus Z worth of charge on an electron out here. And we know already those things hold each other in space at various energies. As we go closer and farther, we've seen different energies. They're continuous energies as you move closer and farther. But now we're going to find if the electron is indeed bounded, there's enough energy to keep it there, then it's not going to be continuous energies the electron can have. It's going to be quantized energies the electron can have. So a bound wave property has quantized energy levels. They'll be described by quantum numbers again. The principal quantum number, n is 1, 2, 3, just the integers. That corresponds to the total energy. And you can always tell the total number of nodes is n minus 1, which will also be the maximum value of L. We said the maximum value of L would tell you the number of nodes. So that quantum number L, we're going to call the angular momentum quantum number. Don't worry about that complicated name. I'm not even going to get into why it's called the angular momentum quantum number. For us, it's just a name. That's a lie. I might say a little bit about it, but you won't be responsible for why it's called that. It might just be interesting to, it might give you some insight to see why it is. The L quantum values, the values that L can have, start at 0, like we saw before. They just count up until they get to n minus 1. So there are multiple values. For every n, you have multiple L's. We saw that earlier. And the biggest one you can have is n minus 1, and that's the total number of nodes. The L will tell you something about the angular nodes, and that kind of tells you something about the shape of the orbitals. The shape of the wave functions. I'm going to start calling them orbitals. Orbitals is just another word for the wave function in this spherical system. So orbital wave function, I'll use those interchangeably. Angular nodes are given by the value of L for each system. So if you have L equals 0, 0 angular nodes, but you might have 4 nodes altogether. All you're saying is none of them are angular. The others must be radial. So the value of L is the number of angular nodes for each wave function individually. Then we'll have this last quantum number, m sub L, and n sub L is, this is getting more confusing now. It's going to go from values of minus L in integer steps. So it goes from minus L to 1 higher than that, to 1 higher than that, along the minus, and then it gets to 0, and it goes to plus values. So if it's easier to just say it, if L is 2, then m sub L goes minus 2, minus 1, 0, 2, 1, 2. So it goes from L minus L to L in integer steps. It's funny when you say integer steps, nobody knows what you're talking about. It means the counting numbers, integer steps. We have a badminton club, and when we play outside and there's wind and stuff and sun in your eyes, we switch sides. And I proposed that we should switch sides after every 5 points. And so I said, whenever the score is an integer multiple of 5, we should switch sides. And nobody had any idea what I was talking about. It just means when you can divide 5 into the score and there's no remainder, so it's an integer multiple of 5, then we switch sides. One of the people said, oh, integer multiple of 5, that's a great name for a band. So I'm sure this happens to you guys too. You start talking. I like to use very precise words, and sometimes people don't understand me because I'm using very precise words and not enough regular words to get the point across. So stop me if I say stuff like integer multiples of 5 and you don't know what I'm talking about. The m sub L, tells me something about the orientation. So I'm going to have angular nodes. What orientation are the L kind of describes, m sub L kind of describes how the planar and angular nodes are arranged. So let's look at orbital energies then. We'll have the principal quantum numbers, 1, 2, 3. The energy of the energy levels is going to go like z squared, and there's z squared there, minus z squared, because we kind of saw this expression already. We talked about what is the attractive force when we did our 2-point system. So they were attracted together. We said, this is high energy, this as they come together is low energy. We pulled them apart, we had to put energy in. We brought them together, energy was released. That's reflected here. So this is the charge. It's z squared because there's a plus and a minus charge. Multiply those together, you get a square. The minus sign stays, plus times a minus. Positive proton, negative electron. Over n squared, and n squared is something like the description of the radius, the energy, the overall size. So this is like the r over r parameter. Bigger n, bigger r in general. So that kind of looks familiar, like the electric potential we were talking about. And I used to tell you it's just proportionality. Well, there is a proportionality constant we can put in here. And this constant's called the Rydberg constant. So I'll give you that value. It's incredibly small, as you might think, but still hundreds of billions of times bigger than h, Planck's constant. So 2.1 times 10 to the minus 18th joules, that's for a single particle. If you take a mole of particles, then it brings it up to kilojoules per mole of electrons. And that's because the mole is so darn big. You get from, I don't even know what 10 to the minus 18th prefix is. itty bitty joules to kilojoules. So, but that's how big Avogadro's number is. You multiply a little number by Avogadro's number and you get a big number. So let's just kind of plot them out. N equal 1 will be the first one. Just put 1 in there and you get the energy. So this is minus R. We're going to have Z equal 1 because Z is the charge on the nucleus. So this is like a hydrogen-like system. So Z equals 1, N equals 1, minus R is the energy. So that's for N equal 1. 2, now I have still Z equal 1. I'm still talking about a hydrogen atom. But now N is 2, so 2 squared is 4, so it's 1/4 of a Rydberg for that energy level, minus 1/4 of a Rydberg relative, and you can go on up the way. And we've seen this before. When we said, I'm going to pull those guys apart, what I said is the farthest apart. So when N goes to infinity, that is R goes to infinity, you're as far apart as possible. That's the ionized state. You've pulled the electron all the way off. The ionized state is the state with 0 energy. We call that the 0 energy state. These other states are below that. So the lowest energy state, the ground state, is a low energy state relative to 0. Okay? 0 just happens to be the top here. And we can set that arbitrarily. We can arbitrarily set our 0 in any system we want. This is a convenient 0. And I think you can now see why it's a convenient 0. It's a convenient 0 because all the energy levels will be below that. You could compare that to our standing waves. Oops, sorry, I have to run through the animations again. I just want to do a quick comparison to the standing waves on a string we had here. Here, 0, we chose 0 to be 0 in energy, and all the energies were positive. And that just gave us an easy point. There's no boundary you can get up here because the energies keep getting bigger. So the best boundary, the best place for 0 is down here at 0. So 0 potential energy. In a sense, this axis is flipped over for this one. You're going to lower energies here, and here you're also going to lower energies, but the lowest you can get is 0. Here, for goodness sakes, here you're starting at 0 and going to lower energies. Also notice the spacing is different. So this spacing is n squared over r squared. This spacing, as you recalled, was n squared over L squared. So a different spacing in terms of the values of n. So let's think about that for a minute. Hydrogen-like energy levels. So which ion does the energy level diagram X correspond to? So this is hydrogen. This is the one we were just drawing. 1 proton, 1 electron, has this quantum energy levels. Here's some other atoms, and I'm just going to tell you these are ions, and I'll tell you Z for each of these. You might not have a periodic table in front of you. I should have one. Z, the number of protons in a hydrogen atom, I think you know is 1. Helium is the second element on the periodic table. Z is 2. And lithium, Z, is 3. So with that in mind, think about this on your own. Which energy level diagram is this if this is hydrogen? And let's talk about that in groups right away. You don't have to, we won't do 2 discussions on this one or an individual and a group discussion. I'm not going to walk out of the room because I do not want my earpiece to disconnect. So I won't come in and join anybody this time. Talk about it amongst yourselves. We'll see what the consensus is. Are you ready?
Do you want to be muted first?
No, I don't care at this stage. I just don't need to talk. You can mute me.
Oh my goodness.
We lost the HDMI connection?
Evidently.
Did just a cable come loose or something? Go ahead, go out of full screen PowerPoint. And I'm going to go back to you. You ready? It doesn't matter what you're showing. I'm just going to go back to you. And yeah, the connection's not there. And it's kind of telling us the connection is not. Oh, there it is. Don't worry. Okay, so most of us are thinking that B is the right answer there. So let's go back to the chem quiz. You're saying B, helium. So you're saying that this energy level dropping down here sounds reminiscent of this Z equal 2 here. And I agree with you in a certain sense. This is a Rydberg here. We're going to go down below that by a certain energy because Z is now 2. So my energy, which goes as minus Z over N, goes down as you've predicted. So we can just go through it here. There's the energy. This can either be 1 for this case or 2 for that case. Minus is still there because there's still 1 electron. It's helium plus. That means there's only 1 electron there. Lithium plus 2, only 1 electron. So the charge on the nucleus is changing. So this thing is getting bigger. N and R are going to stay the same. So I'm going to have 2 here. So I'm going to have 2 squared 4 over N squared, which is still 1. So I'm going to go down to low energy there. If I want them to be equal, then the 1 state for hydrogen is going to line up with the 2 state for something that would have Z equal 2. So 1 over 1 for a hydrogen, 2 over 2 would line up over here. And if 2 over 2 lines up, that means Z must be 2, and that's your helium. Okay, let's do one more. Hydrogen atom transitions, and again, we'll just do one vote on this. Which transition in helium plus, so we've looked at helium plus now, has the same wavelength as 2 to 1 in hydrogen? So I think we're gonna get this one quickly if we just go back and look at the other chem quiz. But talk about this amongst yourselves and see, comparing helium to hydrogen, 2 to 1 in hydrogen, what's that happen? What's that equal to in helium? I wonder why that is. Yeah, I see the result. I want to know the reason. Always want to know why. Okay, we have about 88 voters. Go ahead, push your button if you haven't so far. We'll see what you're thinking. We got about 90, 95 people coming in here. Once we get the fancy cable, I'll be able to go over there and just do that. Okay, that's 99 people. Ryan, show us what the distribution is. A lot of us are thinking C, and I think understand what you're thinking there. So you're saying that the energy level 2 to 1, what does that line up with on a system that looks like this? Well, we have 1-2 spacing, looks like the 2-4 spacing because of that squared factor and the fact that we've gone up a factor of 2 in the atomic number Z, the number of protons Z. Okay, we'll kind of stop here and talk about apply this directly now to chemistry. We've done it simply so far, just talking about the charge of the nucleus and the energy levels. We'll talk about the actual shapes of those wave functions starting next time. Ryan, does that get us, or Melissa, can somebody tell me, does that get us to where we thought we'd get to shielding before the exam?
Oh.
Right? We didn't. How far behind are we? Are we 2 behind?
No, I don't think we're 2 behind, actually.
If we're 1.5 behind, it's perfect because I'll do that on Wednesday. Okay, sorry. I'm just chatting with Melissa about where we wanted to stop for the exam. so I can decide where to stop today. I think it's safe to stop here today. Any questions in the last couple of minutes? What today?
We have multi-electron.
Oh yeah, we have 2 full fall lectures left. Yeah, so we won't get through both of those tomorrow. We'll just adjust the exam. Are there any questions? If you can still hear me, you can comment on the live stream chat. I may have completely lost you, as we thought we might with the different language. Yes, and I'm speaking English, not Minnesotan.
Math won't be that important for the exam, right?
The question is, math won't be that important for the exam, right? I think Ryan was reading that inflection into the text. Okay, so you kind of getting to know me a little bit and my style, and that is, I don't want you to struggle with math and that to make you struggle with showing me you understand concepts. I want you to show me you understand the concepts, and I don't want math to get in the way. So you will find on my exams that math is less prevalent than in other chemistry exams, but it is going to be there. You still have to know how to calculate the energy of a photoelectron. So you have to be able to understand that equation, and you have to be able to understand what that equation means. That's more important to me, and that's why I ask you these graphing questions. You can answer the graphing questions. There's more in that process than plugging in numbers to that equation. When you're doing your homework, you're plugging in numbers to that equation. But there are some homework and there's some chem quizzes that you can review. You can review all of these chem quizzes. They're all online. So that's the general philosophy. I keep it the math as low as possible. I don't want you to do any complicated math, but any equation that you encounter in your homework, you should be able to understand how to use that equation mathematically to put in numbers. Yeah, that's the general idea there. There was something else I'm going to say, math, equations. Oh, there'll be an equation sheet attached to the exam. So we know you're online, and we'll tell you your academic integrity is important to us and to you, I hope. So you'll answer an academic integrity. You're not sharing a screen with someone. You're not sharing answers. You're not working things out. All the work you do is your own on the exam. And we'll give you an equation sheet that has every possible equation that you need to know. And let's post that like now so they can be familiar with it, so they don't have to struggle. We'll post it now so you can use it when you study, so you know where the equations are and you're not sitting there searching it on the day of. So we'll post that. It'll be the same for the entire year. Year is a bad number. For the entire 8 weeks, we'll use the same equation sheet. So everything you need to know will be there. And for a long time, there will be nothing that I ask you that can't be found there or here, I hope. So that will post right away. Using the internet while you do this is against the rules. Can't completely prevent you from doing that. However, recall that B courses, you're going to take the exam in B courses, and B courses has the big brother feature. It's a little spooky, actually. So if you are switching windows a lot while you take the exam, B courses notices that. It notices that you leave the B course tab. So if you're doing that a lot, we'll be able to track that. And it's only fair to say that in advance. So use your academic integrity. Don't have Zoom open. Don't be talking to anybody else. Use the equation sheet as much as you possibly can. Other resources on the internet should not be used. Here's how we're going to do it. We're going to write the exam so that you need all the time just to do the questions. You're not going to have time to search the internet to do things or to call somebody up. Okay, other things?
We're having a review lecture Monday.
The lecture Monday will be all review. No new material on Monday. So we will do. We'll have lots of discussion. There'll be lots of chem quizzes that are broader in scope that make you think of everything from the beginning to the end. Oh, and I will say one other thing. We talked about energy a lot, and we talked about work, energy, balancing. The exam will be rather light on that. What I wanted you, the reason we did that is so you guys could understand when we got here about pulling things apart, putting work, energy in to separate things, and energy level diagrams make sense with delta E's. So the most complicated thing you'll see on the exam would be something like, well, this system did some work and it absorbed some heat. You know, how much energy did it use? Well, how did its delta E change? But most of the energy things, you're just going to be using as background for the rest of the problems. So don't focus on energy balance thermodynamics part. That was lecture 2 or whatever that was. Focus on the rest of the material. So stoichiometry, the general structure of atoms, the ideas of quantum mechanics, how things are arranged and quantized, how matter is arranged in groups. What does the amount mean? What does the density of a substance mean? Remember, gases of same volume have the same number of particles. A mole of particles, if you have two things with a identical relative mass, that's the same number of particles. Those kind of things. And the quantum mechanics we've done here is what you'll have to know. Other things? Okay, guys, off you go. And we will see you again here tomorrow. Same bat time, same bat channel.